All right, let's take a look at chapter 3, section 3.3. We're still looking at building the truth tables for the 5 connectives. This time we'll be looking at the connectives of the conditional and the biconditional. We'll want to construct truth tables for the conditional statements, identify logically equivalent forms of a conditional, use alternative wording to write conditionals, construct truth tables from biconditional statements. In order to understand when a conditional statement is true or false, consider this example. Mr. Gates, the owner of a small factory, has a rush order that must be filled by next Monday, and he approaches you with this generous offer. If you work for me on Saturday, then I'll give you a $100 bonus. If we let W represent you work for me on Saturday, and B represent I'll give you a $100 bonus, then this statement has the form if W, then B. We must examine 4 cases to determine exactly when Mr. Gates is telling the truth and when he is not. Case 1, W is true and B is true. You come to work and you receive the bonus. In this case, Mr. Gates certainly made a truthful statement. Case 2, W is true and B is false. You come to work and you don't receive a bonus. Mr. Gates has gone back on his promise, so he has made a false statement. Case 3, W is false and B is true. You don't come to work, but Mr. Gates gives you the bonus anyway. Think carefully about this case because it differs from the way we tend to use the if-then in everyday language. When you listen to Mr. Gates, do not read more into his statement than he actually said. You do not expect to get the bonus if you did not come to work because that is your experience in everyday life. However, Mr. Gates never said that. You are assuming this condition. Remember that in logic, a statement is either true or false. Therefore, because Mr. Gates did not say something false, he has told the truth. Case 4, W is false and B is false. You don't come to work and you don't receive a bonus. In this case, Mr. Gates is telling the truth for exactly the same reason as in case 3. Because you did not come to work, Mr. Gates can give you the bonus or not give you the bonus. In either case, he has not told a falsehood and therefore is telling the truth. The conditionals truth table for a conditional statement, if P then Q, statement P is called the hypothesis and Q is called the conclusion. If we look back at the truth table for a second, here they summarize the 4 cases. So we have true, true, the result was true. We had truth leading us to a false conclusion. That was a false statement. And when the premise wasn't even true to begin with, it didn't matter what the conclusion was. So the statement itself was true. And that table then summarized what the 4 examples were that we had before. But that's the general form of the conditional. And notice the only time we have a false is when we have the truth leading us to a false conclusion. So if a true premise leads us to a false conclusion, that's the only if-then statement that we have a problem with. For a conditional, If P then Q, statement P is called the hypothesis and P is called the conclusion. A conditional is false only when the hypothesis is true and the conclusion is false. Construct a truth table for the statement not P or Q implies not P and not Q. So here, let's take a look. We have not P or Q. This will be our step 1. Then we have not P and not Q. This will be our step 2. Step 3 will be to take the results of step 1 and the results of step 2 and look for the truth table results for the if-then statement. And this will be step 3. All right, in the truth table, we always begin with a P and a Q. P is always T, T, S, S, and Q is always T, S, T, F. We need not P for step 1, and we need not Q for step 2. Not P is to look at the P column and negate the truth values so that the T's become F's and the F's become T's. And not Q is to look at the Q column and negate the truth values, making your T's F's and your F's T's. Now, step 1, our left-hand side, is not P and Q. Not P and Q are these two columns starred. What we want to do is put an OR between our Q column along with the not P column. This will be our step 1. ORs are only false if both components are false. Both components are false here in the second line only. So our results for step 1 are true, false, true, true. Step 2, which I'll try to make more space, is not P or not Q. That is, we focus on the not P and the not Q column, and we AND them. The AND is only true when both components are true. That's only the 4th line. So we have false, 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 true. Now, step 3 is the entire statement, which I've run out of room for. But not P or Q implies not P and scoot it up a little more even. Okay, go with Step 3 is not P or Q implies not P and not Q result to follow. All right, now in looking at this, what we're doing is we're taking step 1 and step 2, and we're looking at the truth table results. If we ever have a true hypothesis leading us to a false conclusion, that's the key problem. That's false. Otherwise, nobody is told a lie. So if the premise isn't true, you can't have possibly lied. If we have a true premise leading us to a false conclusion, that's a problem. Truth to truth is definitely something doable. So our answer is FT, FT. Let's take a look at their answer. Because there are two variables, P and Q, the truth table has 4 lines. As usual, we will first consider the order of operations as we indicate above the table. All right, now they've done a little mixture of the method 1 truth table and the method 2 truth table. They have some starting convention table line columns, but then they didn't bring up the not Q until they needed it in step 2. But otherwise, they're following the conventions of the first method they showed us. Also, look at the final answer, FT, FT. Notice that in line 1 and 3, there is a true hypothesis and a false conclusion. Derivatives of the conditional. The inverse, converse, and contrapositive are 3 derived forms of a conditional. We can derive the following statements from the conditional, if P then Q, by flipping their positions, flipping their truth values, or both negating and switching their positions. The converse has the form of if Q then P. The inverse has the form of not P implies not Q, or if not P, then not Q. The contrapositive both switches position and negates the truth value. I didn't switch the position. Not Q, not P. That look funny. Converse is to convert or just to move, right? So you just move their location. The P gets moved to the back. The Q gets moved to the front. Converse, convert, move. Invert is the root word of the inverse. And there you're flipping what was white to black and what was black to white, like in our Venn diagrams for set theory. So in set theory, if this is A, then not A is to invert the shading. So what was shaded is now not shaded. So inverting is to negate, right? So when we negate where they sit, we just invert their truth values. So inverting versus converting. And then contrapositive kind of sounds like two words. And we do both the switching the positions and flipping the truth values. The following table will help you remember how to construct these derived forms of a conditional. The conditional is always in the form of if P, then Q. Converse is to switch the P and Q. Inverse is to negate both P and Q, but don't switch. And contrapositive is to negate both P and Q and also switch. Write in words the converse, inverse, and contrapositive of the statement. If marijuana is legalized, then drug abuse will increase. Solution. To understand this problem better, we first write the statement symbolically as if M, then D, where M stands for marijuana is legalized and D stands for drug abuse will increase. Next, we write each of the derived forms symbolically. To form the converse, we switch D and M to get the form if D then M. Translating this into words gives us if drug abuse will increase, then marijuana is legalized. To form the inverse, we negate both M and D to get the form of not M implies not D, or if not M, then not D. If marijuana is not legalized, then drug abuse will not increase. I read that wrong. If drug abuse will not increase, then marijuana is not legalized. Oh, I see. Sorry. I switched the page on myself. Okay, let's go back. If marijuana is not legalized, then drug abuse will not increase. Clear that screen and then move on. To form the contrapositive, we negate both M and D and also switch to get the form not D implies not M, or if not D, then not M. We write this as if drug abuse will not increase, then marijuana is not legalized. Which of the statements, the converse, the contrapositive, the converse, the inverse, and the contrapositive are logically equivalent? Sorry. Okay, if P, then Q, that's our conditional. If Q, then P, that's our converse. If not P, then not Q, that's our inverse. And not Q implies not P is our contrapositive. And we'll show using truth tables that the conditional is logically equivalent to the contrapositive. And you can also show using truth tables that the inverse is logically equivalent to the inverse. The inverse and converse are logically equivalent. The conditional and contrapositive are logically equivalent. The two that have the word verse in it are logically equivalent, if that helps. We will answer this question by comparing the truth tables for these statements. We can see from the table that the original condition and its contrapositive are logically equivalent. Neither the converse nor the inverse is equivalent to the original conditional. However, they are equivalent to each other. So using the truth table, you can see that the truth table results for the conditional match the truth table results for the contrapositive, and the truth table results for the converse match the truth table results for the inverse. Alternative wording of conditionals. Q if P. Here, the if still is associated with P, even though it occurs later in the sentence. P only if Q. Recognize that only if does not say the same thing as if. The if condition is the hypothesis. The only if condition is the conclusion. P is sufficient for Q. The sufficient condition is the hypothesis. Q is necessary for P. The necessary condition is the conclusion. Example of rewriting statements in the if-then form. We write each statement in the if-then form. Your driver's license will be suspended if you are convicted of driving under the influence of alcohol. If you are convicted of driving under the influence of alcohol, then your driver's license will be suspended. You will graduate only if you have a 2.5 grade point average. If you graduate, then you have a 2.5 grade point average. To hold your reservation, it is sufficient to give us your credit card number. If you give us your credit card number, then we'll hold your reservation. To qualify for a discount on your airline ticket, it is necessary to pay for them 2 weeks in advance. If you qualify for a discount on your airline tickets, then it is necessary to pay for them 2 weeks in advance. Let's look at their solutions. Your driver's license will be suspended if you are convicted of driving under the influence of alcohol. Because the if goes with the clause, you are convicted of driving, that clause is the hypothesis. We can rewrite the sentence as, if you are convicted of driving under the influence of alcohol, then your driver's license will be suspended. You will graduate only if you have a 2.5 grade point average. The only if goes with the clause, you have a 2.5 grade point average. Therefore, this is the conclusion. We write the sentence as, if you graduate, then you have a 2.5 grade point average. To hold your reservation, it is sufficient to give us your credit card number. Then the phrase, it is sufficient, identifies the hypothesis. We write the sentence as, if you give us your credit card number, then we will hold your reservation. To qualify for a discount on your airline tickets, it is necessary to pay for them 2 weeks in advance. Then the necessary condition is the conclusion. Rewriting the sentence, we get, if you qualify for a discount on your airline tickets, then you pay for them 2 weeks in advance. The biconditional means that two statements say the same thing. We symbolize the biconditional as the P with the double arrow and then the Q, or we read it P if and only if Q. The biconditional is true if both P and Q have the same value. So if both components are the same, the biconditional is true. If the components are different, the biconditional is false. Construct a truth table for the statement not P or Q, if and only if, not Q or and P. So first, we make ourselves a P column, a Q column, and then we answer inside the parentheses of the left-hand side. P or Q is only false when both components are false. To negate this, we then look at the whole column for P or Q, and we negate each entry. Then to do the right-hand side, we need not Q, so we develop not Q. Inside the parentheses, which make up the right-hand side, we have not Q and P. Not Q and P is only true when both components are true, which happens in the second line. Now, take your results for step 1 and step 2 and apply the if and only if bi-conditional rule. That if the signs are the same, the statement's true. That happens in line 1 and line 3. In line 1, both step 1 and step 2 yield false, and in line 3, both step 1 and step 2 yield false. Otherwise, false true or true false.